This is the second of 3 videos on Newton's laws of motion. In this video, we're going to continue talking about forces, and we'll also talk about Newton's third law. So forces, once again, are vectors. That means that they have magnitude and direction. When we have more than one force acting on an object, the net force is the vector sum of those two forces. Here we have an example of a satellite being pushed on by 2 astronauts. Astronaut 1 pushes with F1 to the east, only in the x direction. Astronaut 2 pushes with F2 up at an angle of 52 degrees. So that second force, F2, has an x and a y component. He's pushing it to the east with F2 times cosine of 52 degrees, and he's pushing it upward with Fy equal to F2 times sine of 52 degrees. If I wanted to find the net force, I would find the vector sum of those two vectors. And that would mean that I would need to use component addition to find that total vector, magnitude and direction. So, here are a couple of examples. So if I have a force that's written in unit vector notation, like this, F equals 20I minus 60J newtons, and it's applied to a 10 kilogram mass, if I'm asked to find its acceleration in unit vector notation, then I'm going to approach this the same way I have in the previous problems. I'm going to start with F equals ma, and I'm going to solve for A. A is equal to the force divided by the mass. But in this case, if I'm pushing to the east with 20 newtons and to the south with 60 newtons, my acceleration is also going to be to the east and to the south. So I'm going to apply Newton's second law in both directions. I'm going to find the acceleration in the x direction by taking 20 newtons and dividing it by 10 kilograms, and in the y direction by taking negative 60 newtons and dividing it by 10 kilograms. So when I do that, I find that its acceleration is equal to 2I plus negative 6J meters per second squared. If I wanted to find the magnitude of this, then I could use Pythagorean theorem because I have the x and the y components, and I could take 2 squared plus negative 6 squared and take the square root of it. If I wanted to find the direction of it, then I would use tan theta equals y over x. In this case, the inverse tan of negative 6 over 2 is negative 72 degrees, which tells me that I'm not in the first quadrant, and in order to make this a polar coordinate, I need to figure out what quadrant I'm in. I have a negative y and a positive x, so I'm in the fourth quadrant, so I need to take the 72 degrees off of the 360, and my heading would be 288 degrees. It's important to note that the acceleration and the force have the exact same direction always, always, always. If the total force were to the north, then it would accelerate to the north. In this case, if the acceleration has a heading of 288 degrees, then the force was pushing, the net force was pushing in the same direction, 288 degrees. Also, remember that if I have several forces acting on the object, like in our example with the satellite, that all of those forces have an x component and all of those forces have a y component. Sometimes it's easier to see that when they're written in unit vector notation, as these are. A is equal to 20I minus 40J newtons, B is equal to negative 10I plus 40J newtons, and C is equal to 30I minus 10J newtons. So if I want to find this vector sum of those, the resultant force, all I need to do is add up all the x's to get 40I and add up all the y's to get negative 10J. And my resultant can be written as 40I minus 10J newtons. And then if I want to find the magnitude and the direction, I can use Pythagorean theorem, and I can use tan theta like I did in the previous problem to find the magnitude to be 41 newtons and the direction to be 347 degrees. So remember that forces are vectors, they have magnitude and direction. And the last thing I want to talk about in this video is Newton's third law of motion. His third law of motion says that for every action, there's an equal and opposite reaction. In other words, forces always come in pairs, acting on different objects. If object 1 exerts a force on object 2, then object 2 exerts a force in the opposite direction on object 1, and they're exactly the same in magnitude. These forces are called action-reaction pairs. Let's look at some examples. Suppose you're driving down the road. How does that work? Well, your tire is rotating, and as it rotates backwards, it pushes on the ground in the backwards direction with F, and the ground pushes equal and opposite with negative F in the opposite direction. If you're pushing a refrigerator, your hand pushes on the refrigerator and the refrigerator pushes back equal and opposite on your hand. The reason the refrigerator moves is that the force that you're pushing with is bigger than the frictional force on the floor. The floor's frictional force is not part of that action-reaction pair that we just identified. The action-reaction is between your hand and the refrigerator. And let's look at the cart on the table below. This is a top-down view of you moving a cart along the table. You push the cart, and the cart pushes equal and opposite to you. The action-reaction pair is the cart in your hand, equal and opposite. And then finally, one that's a little harder to see is the reaction force acting on something like the space shuttle. So first of all, let's identify what force is pulling on the space shuttle. The space shuttle is trying to, even though it's in orbit, it would like to fall to the Earth because it has weight. So there's a downward force of weight acting on it. So what is the reaction to that? Well, it turns out that if the Earth pulls on the space shuttle, the two objects are the Earth and the space shuttle. If the Earth pulls on the space shuttle pulls back equal and opposite on the Earth. And even though they're not touching, they're equal and opposite force pairs at a distance.